Thank you, Atif Mahmoud, for the incredible and hype video to start. Okay, Schulich leaders, please get out of your seats. Let's make some noise to launch SLXCA 2019. Let's go. All right. Yeah, sure. Let's go. Let's go. Thank you, thank you. Thank you for joining us. Thank you for joining us to ring in the new academic year in our 4th annual network events, Schulich Leaders Across Canada. I want to thank the generosity of the Schulich Foundation for bringing us together today. To our university partners hosting events in 7 different provinces at UBC, University of Calgary, University of Manitoba, University of Toronto for the after event, Université de Montréal, Polytechnique Montréal, University of New Brunswick, and Memorial University. We thank you for your hospitality to ensure that these invaluable SLX events take place for this gifted network of national STEM scholars. To the tireless efforts of our Schulich Leader volunteers, especially to our network of squad captains and Schulich leaders who stepped up to prepare and give leader talks today. We also thank you. And to our newest 2019 Schulich leaders joining this prestigious network of STEM innovators, let's give a huge congratulations and welcome. So why are we here? This remarkable program has created an opportunity to ensure each one of you can come together and learn and motivate one another. You each have unique skill sets, growing expertise in your STEM disciplines, and a wealth of experience that has brought you to this level as active members of a highly distinguished network of Canadian innovators. As Mr. Schulich often laments about youth, you are rich in age. And we implore you to use this newfound wealth to explore and learn from each other, to chart the best path towards realizing your full potential. This year, the Schulich Leader Network will continue to evolve to provide more resources to optimize your personal growth. Wesley Fink, a 2015 Schulich Leader in electrical engineering out of University of New Brunswick, is taking on a new role as chair of the Schulich Leader Network Development to ensure better connectivity and shared learning among Schulich leaders and our growing alumni network. Whether it is through peer-to-peer or group mentorship, job and career assistance, or enriching the student experience through SL squads nationally, we have an abundance of resources at our fingertips to help accelerate your path to ensure your success. This month, you will gain access to a digital Schulich Leader directory available through a secure portal on our program website. This will be a highly resourceful tool for our network going forward. With an alumni network now of 130 Schulich Leader graduates and always growing, we are launching alumni events in Toronto, Vancouver, and Montreal this year. In June, our foundation and the Leaders Fund, along with the University of Waterloo and Communitech, launched the nation's largest competition in artificial intelligence to help resolve the global issue of fake news. The purse is $1 million to be awarded in June 2020. There is still time to sign up before the Phase 1 solutions deadline of November 18th hits. So we encourage all of you, Schulich leaders, to participate if you are able. Lastly, our Schulich leaders continue to turn heads, impress and inspire notable Canadians and the general public each year. Our desire to align this program with the top minds in our nation is paramount. With that being said, we are so fortunate to have one of the leading Canadian innovators with us today. Fusion power, the power of the sun and the stars. You know, I'm going to save and stop myself right there and save the details for the chief scientist out of Vancouver who's joining us today, but I will tell you this. We are in the midst of a global race to harness fusion power. When we do, and it's only a matter of time, the world will have limitless, clean, and hopefully low-cost electricity that will eliminate carbon emissions from other energy sources and create an electric society. Just imagine. Leading business people and philanthropists like Jeff Bezos, Bill Gates, and Richard Branson have invested their money behind our opening guest speaker out of SLXBC. Dr. Michel Laberge has invested his time and talent to bring fusion power to the masses out of Burnaby, Canada. It is our honor to welcome Dr. Michel Laberge to kick off SLXCA with his presentation, Fusion, Transforming the Way the World is Energized, followed by a Q&A through our Facebook Live comment feed, moderated by Lasya Venkayala, our SL Squad co-captain at UBC. Ladies and gentlemen, please welcome Dr. Michel Laberge.
All right, thank you very much for inviting me. So we have a little problem with energy. I won't go very long about that. You all know about the problem that we have with the squash dinosaur that we're burning and making lots of pollution and CO2. So what are we going to do about this? So if you look at the distribution of energy nowadays, it's those big triangle there, those big three one there. They're like liquid gas, and coal. So this is most of the energy is producing by that. Those are the percentage here. Now everybody's thinking, okay, we're going to solve that with wind and solar. But if you do an extrapolation of the wind and solar, how much we're going to install, you get this graph here that goes all the way to 2040. And you can see the renewable, which is the little purple stripe on the top, is not going very fast, just a few percentage of it. And the big three, coal, liquid, and natural gas, is still using most of the power. The reason for that is because wind and solar is variable. So this is the power produced by wind and solar in California. And you can see on a daily basis on the right there, there's a big peak of solar in the middle when it's sunny and there's no solar. And you can think that perhaps you can absorb that with battery or something, but it's very expensive. But also what you can notice is on the left graph, there's annual variation also. And there's no way you're going to store energy half the year and then put that back on the grid the other half of the year. That's way just too much power. So solar and wind are good to about 10 or 20% penetration, but above that, it's getting very, very expensive and complicated to try to save the day. So we can't really save the day with solar and power, which a lot of people think, but people that know in the know that would be way too expensive to do. So what can we do? There's the good old fission. Fission is pretty good. There's no global warming CO2 emitted. In fission, you shoot a neutron on uranium and it's split in two. It makes a big mess of radioactive material. There's this barium and krypton there. When you do fission, it breaks in different parts and it throws the parts all over the element table, lots of radioactive waste, and it can melt down. So fission, this is very confusing, fission and fusion. Fission is not in love. People are not in love with fission right now, so it's very difficult to install fission. So what else can we do? The sun runs on fusion. Now, what's fusion? The reaction for fusion is deuterium and tritium, which are two elements of hydrogen. Essentially, you fuse two hydrogen together and you make helium and a neutron. Now, helium is what you put in the party balloon. There's no radioactivity. It's fantastic. It's wonderful. And it makes lots of energy. The fuel can be extracted from seawater. There's billions of years worth of fuel in the sea. It's cheap. It's fantastic. So what's the problem with it? Well, the problem is the two pieces. They're both electrically charged, positive. And as you may know, two positive charges repel each other. So they don't want to fuse. In order to fuse, what you have to do is to cook the gas to very high temperature. Solar temperature, 100 million degrees C. At that temperature, the atom go fast enough that they crash into each other and fuse. Now, 100 million degrees C is a bit difficult to handle. So people have been proposing over the year to handle that with the magnetic field. So you put a bunch of ring, put some electrical current, makes a magnetic field that go around in a donut. It's called a tokamak. Now, at very high temperature, the atoms crash into each other. The electron go flying one way. The middle, which is iron, go flying the other way. The particles are charged, and they spin around the magnetic field, and they get trapped in there. So they don't actually touch the wall. So right now, they're building those tokamak. This is the picture inside the tokamak. On the right side, you see this funny purple glow. That's when the plasma is on. And the biggest machine right now is ITER. ITER is a collaboration of all the big nations in the world, but not Canada. And they're building this $20 billion, that's with a B, machine in the south of France. It's in construction right now. And it will start to produce, this is a prototype. It won't produce electricity on the grid, but it'll produce heat in about 2030, if things go well, in about 10 years. And after that, to make a real power plant to make electricity is another 20 years. So that's a bit of a slow progress. It's an international collaboration. People are whacking about which way to put the pipe and the current and the electricity. So it's a bit slow. Another way to do fusion is laser fusion. You take a little pellet, you put your fuel in there, and you shoot a big laser all around it. and you squash the pellet. And when you squash something, it gets hotter. If you do that quicker than the heat loss, you can go to 100 million, and that's laser fusion. This is being built, like this is a picture of it. There's a bunch of laser hitting the little pellet in the center. And this is the NIF, the National Institute Facility. It's about $5 billion in the US. And that have been producing more and more fusion, but it's still a little bit short. It's actually a little bit short of what they were hoping for. But this is another way of making fusion. But both of those ways are very, very expensive. So it remains a bit to be seen if they can make electricity at a good price. Now, most people think about fusion as something that's not doing any progress. Like they've been hearing about fusion forever. We don't have a fusion power plant. Is anybody doing any work on this thing? Is it happening? Well, in red there is the amount of fusion that the machines are producing since 1970. So you can see that between 1970 and 2000, we went 10,000 times more fusion. This is 10,000 times more fusion. So in 1970, they were producing piddly little amount of power, and now they almost break even. The big gray bar on the top is when you produce enough fusion to pay back, because you put a lot of energy to heat it up, and then it produces some energy, and you have to produce more energy than what you dump in. And NIF and ITER are the little dot there. You notice it left a little bit the trajectory as of lately, because those machines are so big that the international collaboration, that's a bit slow. So that have drifted to the right, like to 2030 for ITER, for example. Now, this is compared to the Moore's law. Everybody's very excited about Moore's law, how fast the electronic is. Oh, it's so amazing, the speed of rays of electronic. But check that out. The improvement in fusion up to 2000 was actually tracking how fast the electronic was going. So there is progress being done in fusion. Now, at General Fusion, we want to do something else called magnetized target fusion. But before I talk about that, maybe I will throw a little bit about my life, because I'm supposed to be describing how great student in physics are. So I'll have a go at this. So I did my degree at Laval University, and the reason I did it there because it was a 15-minute drive from my mom's. So it's nice and cheap to do that. And then I went at 25 and decided maybe I should leave my mom's house, and I decided to go to UBC here. And I choose UBC because I like skiing. So I was doing circle around a ski resort, and I caught that UBC was a circle around Whistler. So I came here at UBC to study. Now, it turns out I was the guy that I found to take me to study was doing laser fusion. So this is where I could get exposed to fusion science. So I did a PhD here. I did a postdoc at Paris at École Polytechnique, another postdoc at Ottawa, but that was not on laser fusion. This one was on femtosecond laser, a very short laser pulse. And then after that, perhaps I needed a job. You know, you want to make some money eventually. So it's very nice, all those postdocs, but eventually you want to find a job. And it's not that easy to find a job in physics. There's quite a few physicists that drive taxi and stuff like that. So I found a job at a company here in Vancouver called Creo Product, and we were doing laser printer, big format laser printer for the printing industry. So I did that for 10 years. Works pretty good. They were paying well and everything. And they were giving me something called shares. I didn't understand what that meant, so I threw that in the bottom of my drawer. And then eventually, when I was 40 years old, I got a little bit bored of doing laser printer, had a bit of a crisis. I noticed that the planet needs power, like clean power. And because I was exposed to fusion during my academic year, I say, okay, fusion is the thing to do. But all those academic fusion people, they're going kind of rather slow. They drink coffee, goes to conference, write paper, but they're not very driven to make a power plant. So I say, okay, I'm going to start a company to make that. No, that's a little stupid to make a company out of fusion when you're just working around at the local laser printer company. But I had a bit of shares. And those shares, it turned out they were something because my company got sold to Kodak. And then suddenly the share was a bit of money. So I could actually quit work and do fusion with no salary because I have a bit of money in front. I still have to pay for my wife and kid and everything. So you need a bit of money. But I had a bit of money in front of me. And then I raised a bit of money from my friend because my friend were in the same situation. They had a bit of money from Creo. So I raised about $300,000 from friend and family. There's government grant to help start the little company. So I get about $100,000 from IRAP, another small Canadian fund. And then I start to build a little machine in the garage. And eventually I managed to make a little bit of fusion of my machine, not energy, but a bit of fusion. And then I decided to go a bit bigger. So, okay, with that fusion now, I need to raise money from VCs. So first I needed to hire a CEO because very often, this is a mistake that many people do. They think they're great at doing physics, but they're not necessarily great at running a business. Like, it's not always the same skill to run a business and to run science. A lot of science people will start their business and run their business and crash it lamentably because they're good at science and they're not that great. So at Creo, I had my ex-boss, Doug Richardson, which was quite good at business, I thought. So I hired him with no salary to be my CEO. So I found a guy that was good at business to do the CEO bit while I was doing the science bit. That's a mistake that a lot of people do, by the way. Like, you see a lot of companies run by nerds, and this is not always totally the good way to do it. Sorry, no insult. I have nerds in great respect, but they're not always the good type. Anyway, so this is starting, and we found some money. The first VC to invest were local VC in Vancouver because they knew us. Like, we had a bit of a name in the Creo business in Vancouver, so the local business guy knew that we were good people, so they gave us some money. Now, when you have a bit of money from the first VC, then you can go for other VC, because that bunch is a bunch of sheep a little bit. You know, they like following each other. So once you manage to land a bit of money, then you can get a bit more, and we get more and more. And then nowadays we got some money from people like Malaysia, like the Malaysia fund of money invested in General Fusion. So that's how this company came to be. So I thought I would pitch that in because I was asked to do that. Now let's go back to the physics, which I like way better than that. So what we want to do at General Fusion is magnetized target fusion. And magnetized target fusion is a mix between the two. So you see this little ring in the center, that's a bit like a tokamak. There's a magnetic field in there, it holds the particle together, and then you squeeze it. You put it in the big bucket of liquid metal that you spin around in a circle to make a hole in the center. You shove the plasma in the center, and then you have a big piston around it that squash the liquid and squash it. One of the big advantages of this thing is piston is way cheaper than laser. Like, I was a laser expert, and laser is very expensive. Piston, you know, you get that in your car, it's cheap, works well. So by doing that, I can make this machine very, very inexpensive. Also, the liquid metal will absorb all the neutrons. One of the problems with fusion is the neutron comes out. This is where the energy comes out of the fusion reaction, fast neutrons. And if those neutrons hit the wall, breaks the wall, machine gets broken. But here, I absorb all the neutrons with liquid metal. The liquid metal gets hot. You pump that to a steam engine, and you make some turbines, run some turbine, make electricity. And then some of the steam comes to push on the piston. So the recirculated energy is very cheap. It's the steam right off the boiler. You don't have to turn that into electricity and capacitor and laser and whatnot. So it's a nice, easy system. So what we want to do is something like that. It's a big sphere. It's about 3 meters diameter in the inside. Like, the red part in the center is 3 meters in diameter. It's about yay big. Then we have a plasma generator on the top that makes a plasma, which is a big blob of gas. By firing lots of electricity in it, you turn that into plasma, shoot in the middle. There's the liquid is spinning in the center to open a big cavity. And then there's a whole bunch of piston around it, a bit like syringe. And you fire all the syringe and you shove some liquid in there. And as the liquid gets shoved, the plasma gets compressed in the center. So that's what we want to build. Now, that was not that easy to build. So this is the garage where it started. It's on Boyne Island, by the way. If people know around here, there's a little island just off. This is where I lived at the time, and I wasn't bored of commuting with the ferry. So I think if I start the local garage, that would help. So I built a small machine about this big, get a couple of neutrons, managed to get that going. So here, this is the team. At the time that we would get our first VC money, there were only 6 people. And those little receipt there, that's the $3 million that we managed to land from VC. We were quite excited. So that's the receipt from depositing the money in the bank. And then we started building things. So this is the compression system where those big things are piston. Now, this one's got only 14 piston. That's not enough to make fusion. You need more than that. You've seen the little video before. It was covered with piston. But this was a test rig. See if we can make that work. So we built that. Works pretty good. Then this is the plasma generator. We're not compressing this plasma. We haven't put it in those big piston. But we want to know if the plasma will be hot enough and good enough for a starting thing. So this is called PI3. That's the third one we built. And we shove the plasma in there, and it stays there, and it stays hot and good enough. But we have not built something that includes the plasma and the piston yet. And also, to form the cavity, we have this grid that spin, and the centrifugal force jam the liquid on the outside. So this is in the middle there is the grid that spin and this channel. And then when you fire the liquid goes through the channel to compress the cavity inside. So this is the cavity generating system. So this grid spin, and the centrifugal force jam the liquid on the outside, and you push the liquid through and squash the plasma. There's no plasma on this machine. This is just a liquid testing gear. And what we want to do next is to integrate the two together, actually the three together. We want to, the plasma formation, the grid spinning, and a whole big pile of piston all around that to squash it very vigorously. So this is what we want to build next. This is going to be very close, not quite the scale of a power plant, but very close to a power plant. The problem is we don't have quite the money to do that. I guess money, maybe I should give a little, because money is important, like the sort of scale of money that we raised so far. So over 15 years of operation, we raised about $120 million from many diverse VC. About 20% of that, maybe 20 million, was from government grant, like Canadian government grant. And now, in order to build this big thing, we need a couple of $100 million. So it's a bit of a scale up in expenses. So now that's what we're doing. We're going around with our tie and our suit and our little presentation and go and talk to the banker, try to get some money for it. And then we will build a nice big machine, and hopefully this is all going to work. But finding the money is not that easy. And when I started, I was all myself, but now the company is about 68 employees. And you see the crowd here, that's my company. That's about it. Thank you very much.
Thank you. Thank you. So at this point, I think we're going to open up the Q&A here in the room while we wait for the Facebook Live questions to populate. So do we have any questions right now from here? Yes. Hold on. I'm just going to run over. Let's just make this easier.
Hi there. I'm curious whether you have any fears about promising people a new source of energy that they don't have to be careful with, like whether you feel that we should be whether we should be encouraging people to just wait it out until we have a source of energy that we don't have to feel guilty about, or whether you think that we also have to be changing the way we live our lives on Earth to try and reduce the amount of energy we're using, because the fusion is an incredible idea, and it would be wonderful if we didn't have if we had an energy source that wasn't a pollutant. Yeah. But do you think there's a danger in just telling people, oh no, it'll be fine, just wait until we have this up, and then
yes.
You can do whatever you want?
Yes, people will keep on spending the energy because they say, we'll be safe in the future, who cares? Well, I think that this already exists. People are not reducing power, I'm afraid to say. We all say, let's save power, let's save power. But look around here, the people drive big SUV, they have 2 of them. Their house, they used to be 1,000 square foot, now they have 4,000 square foot. The people are not reducing their energy consumption. They go in Hawaii every weekend, So it's very nice thinking that people will reduce power consumption, but it is not happening. If you look at the number, people are spending more and more energy all the time. And that's all planet too, not just the nice Western comfortable place. People in the smaller country that have not much in the past are using more and more energy. So I think it would be, yes, it would be a problem if the conservation would work. Telling them we'll save the bacon is not good for conservation. But conservation presently, I'm afraid to say, is not working. People are just spending the money. My son, his theory is the gas is going to run out, so I have to burn it while it lasts. So you buy some big trucks and skidoos and stuff, So I don't think we're going to save a lot of power around here. So we need something to save the bacon at the end.
Are there any other questions here? Right. Okay.
This is a little bit specific, but why are you using lithium as the liquid?
That's interesting. Did I say that I was using lithium? Anyway, yeah, in the machine. Well, lithium will actually rebreed the tritium. Like you need deuterium, tritium. Tritium's radioactive, 11-year lifetime. There's no natural tritium, so you have to rebreed it. So what you do is in the liquid, there's lithium. When the neutron hit the lithium, it breaks in 2 parts. It makes helium that you let go up the chimney, and tritium that you put in the machine and burn. So there's no incoming or outgoing of tritium, but there's a small closed loop of tritium being rebred and reused. And that's why you need the lithium. It also needs to be a liquid metal that doesn't melt too hot. And it has to be electrical conductor in order to compress the magnetic field. So liquid lithium is good for
that. A quick question about business, maybe.
Sure.
Even though it's not your favorite subject.
I have people doing that for me now, but I did it at the beginning.
So a big part of raising all this money you had said was venture capitalists.
Yes.
How do you convince people to give you and donate money when you don't have a return yet?
Yes, it's a fairly long time return. So that cut out a lot of VC. Lots of people want a quick buck, right? Like they invest in apps because you put 6 guys in a pizza and they work for 6 months and poof, the apps come out and you make millions. This is a little longer, but some people have a bit longer, and some of them think that perhaps it'd be good to save the planet, maybe. That it's good to save money, they want to make money, but some of them, like they have a bit of the, okay, maybe I should try to do something nice, you know? Because the app, you know, it's great, make big buck quicker, but it's not always saving the planet. You know, tweeters, do we really need that? Anyway, so you do find VC, but it cut down an awful lot the number that would be interested. So the amount of VC that you have to knock at the door with your little presentation is very high. We hit maybe 1%. So for 100 pitch, we get 1 guy to invest. So it's hard work to sell that. And yes, the long time is one of the things that most people say, this is too long, I'm not going to go for it. But you can find some people that have a bit of a longer time scale.
We're going to take a couple questions from other sites and then we'll come back here. Just a reminder, when you're submitting your questions on the Facebook Live, please tell us which university you're from and which event you're coming out of so we get an idea of the scope of where the questions are coming from. So Miranda?
Jack from the Schulich Network asks, is the only thing holding back fusion currently funding, or is it scientific advances as well?
Oh, the basic understanding of fusion is quite high. So we know fusion will work. It works on the sun. It works actually on thermonuclear bomb. That makes a lot of fusion energy. There is some science left because people do fusion different way, and the way we want to do is a bit different than other people. So there's some science there. So it's not a done deal. There's still some science. But I would say that right now, our general fusion, our immediate problem is money. But finding the money for it is actually as hard as doing the science. I would say it's a 50-50 thing between the money. Fusion doesn't have a good rep. Like, if you hear about all the solutions for global warming, do you ever hear about fusion? No, you hear about wind, solar, chicken shit, whatever, but never fusion. So it's difficult to find money for fusion, that's for sure.
Lasia, can we ask a question
And
from
Kennedy asks, what
SLX
advice
on
would you give Schulich leaders interested in physics?
Physics. Physics is a little difficult. There's less job in physics than in engineering. When I was a nerd, so I knew I wanted to do something technological, and I didn't know if I would go in engineering or physics. And all my buddies were going in engineering, but I said, this is boring. Like everybody does engineering. I'll do physics because it's different, just to be a bit annoying. And I got lucky that I had a good, successful career in physics. At the time, physics was difficult. A lot of physics were taxi driver. Now physics is better, actually. I think there's much more science and technology, and companies are starting to recognize physicists as being good system guy. You know, they're not as good as an engineer to make like a piece of metal or a piece of software, but as a system engineer, because a physicist know a little bit about a lot. An engineer know a lot about less, right? So the physicists are a good generalist guy, and that has been recognized. So now physicists have a better chance of finding a job in the industry. And you have to go for people that build stuff that are a bit complicated with many things, because you're going to have to compete with the engineer, those pesky little engineer guy, And the engineer, you need a project that's a bit wider than what a single engineer field of view is. Otherwise, you're going to lose. Like if you try to beat an engineer on the engineer bit, the engineer knows more than you do. But for sort of system thing, it's good to be an engineer, physicist.
Lasia?
Jacob asks that what kind of advances or breakthroughs in fusion have you seen recently that shows that we're headed in the right direction with fusion?
Yeah, what I find interesting, those tokamak guys, most of the fusion work is on the tokamak, this big donut magnetic field. So there's something that's called a scaling law. Is how long does the heat stays in there? Because the heat is very hot and there's turbulence and the heat escape. And they're fighting that for a long time. And the approach they use for ITER is to make a bigger machine, because a bigger rock takes longer time to cool down than the smaller rocks. So they build a big tokamak and they think the heat will escape slower. But people with smaller tokamak keep hacking at it, and the actual speed at which the heat escape is getting better and better. So nowadays, if you would use the best heat loss, you wouldn't have to build a ITER size. It would work smaller. So basically, the the confinement, the amount of heat retention that you get out of this machine is getting better all the time. And the latest machine, there's a result that comes every year. Oh, getting better, getting better. So basically, if you keep chipping at a problem, it slowly gets better and better. And fusion's like that. So nowadays, with the latest result in heat confinement, you would not really need to build such a big machine. So a smaller machine. But our scheme is much smaller for different reasons.
In terms of actual like deployment of the system, so
Yep.
let's say that you raise the funding, you get your big new machine. Can you talk a little bit about the hoops that you'd have to jump through to get the technology to be accepted and be used to power everyday things in our lives?
Yes. So what we're doing there is we're trying to do the core of this machine. So we're not doing turbine and heat exchanger and all that thing. So when it's time, when this work and it's time to make it happen, we will probably have to deal with a big company. Like power plant are big machine. Like a little company in Burnaby don't build like those big. So you will have to have a collaboration with General Electric, Westinghouse, Hitachi, one of those big guys that makes power plant. So those guys will deal with the steam turbine and the transformer and the electricity and the building and everything. So General Fusion will provide the center core, and those big companies will provide the rest of the machine. Now, after that, it's the ramp. It would be nice to instantly replace all the energy on the planet by fusion, but this is not realistic. The installed base of energy on this planet is huge. It's like terawatt of power installed. So even going flat out, what you're going to pick up is those piece of pie at the beginning. The fusion piece of pie will grow slowly, and it will take, many years until it swallows up the whole power. So it's going to be a slow ramp of installation. So we're going to burn some carbon for a long time, in my opinion. Like even if fusion works according to plan, it will start to pick up and slowly grow and eventually displace the carbon, but that will take a long time.
Now we're going to be taking some questions live from Toronto. They're very excited. They want to actually ask through the mic. So just give us a second to stream that out. And then we'll come back here. I know I saw a lot of people with questions.
Okay. Hi, my name is Jacob. I am a physics student from Queen's University. I asked a question earlier, but I had a bit of a follow-up on it too. So I was wondering if you had any insight on other countries, such as China, on how they're doing in terms of nuclear fusion progression.
Yeah, China is a member of ITER, so they pay their due and they are making the big ITER project. There's a percentage of China, but China is very impatient with ITER. ITER has been very slow because it's an international. So ITER is building their own project. They got 600 million for design. And when they finish their design, they will probably get the billion required to build it. So I think ITER will be, China will be the first country that will produce a power generating tokamak. Now, I still think that tokamak's the wrong way to go. It's still going to be big and expensive. So the cost of electricity, I think, will not be very competitive because it's too big. Our system is better. But I think China, they're putting lots of resources, lots of effort. And I used to say that was a bit of a joke, but we thought that China would make a tokamak to make fusion before ITER have installed the washroom. Because, because like the ITER is going very slowly. It's a bit of a disaster project management one. And China, they're really going for it. They're putting the money, they're putting the effort. I think they trained 2,000 plasma physicists in China. They're going for it. China will make fusion happen, but the standard way. The thing with China is they're not very innovative. They take what exists and they do it fast and they do it cheap, but they're not that great of thinking outside the box. And I think the company that, and by the way, General Fusion is not the only company. There's now dozens of companies doing different way of doing fusion. We're the best, but there's others. And China on the big tokamak normal way, I think they will be the first, and they're pouring quite a bit of resources into it.
Another question from Toronto. We wanted to know realistically how far away we are from realizing fusion energy and using it.
Okay, my normal bracket is we're gonna have a fusion power experimental producing a bit of electricity on the grid between 10 and 15 years from now. Now, if you ask most of the physicists in the big fusion, like the big ITER people, they're less optimistic than that. They'll give you 50 years or something. But I think because the industry is starting to jump in, there's a lot of company going with innovative stuff and General Fusion because we're the best. We will put an electron on the grid in 10 to 15 years, in my opinion. Maybe not us, like we only have 60% chance of success or something, but if you have 10 companies at 60% chance of success, somebody will crack that nut. Planet needs it, and it's gonna happen. 10 to 15 years is my prediction. This is not gonna make a big dent in the energy, right? This is the first machine producing a bit of electricity. After that, there's a long wedge to build that. That'll be long. So we're a bit late for the global warming. The planet's gonna get some shit. Yeah, I would have said the same thing 10 to 15 years ago, correct. Actually, I think it's a matter of fact I did.
Are there any more questions out of Toronto, or should I take it back to the room here?
One more from Toronto, from David Stein.
Good afternoon. Can you talk a little bit about just what you think the relative difficulty is between the effort that went to solve fission and make it that commercially viable versus fusion and kind of the order of magnitude and just some historical context of how long that took to solve versus what you're working on?
Yeah, fission went faster, I think. Technically fission is a little easier to do. But I think they were a bit of a better incentive for fission. Like fission technology was developed by and for the military. Like you're all aware of the atomic bomb, Los Alamos little plant there. So they pour a huge amount of resources developing that. And after that, they needed a reactor for the submarine, actually. Like what make fission reactor, not fission bomb, happen is a submarine. There's an Admiral Rich Stoffer there that went with a whip and whip everybody in shape and focus the project, and they made it happen. So I think it was a little bit easier fission than fusion because the high temperature and the turbulence, that's a little bit more complicated. And B, they were a big incentive from the military. They were pouring the resources. When they do the Los Alamos project, this in today's year was probably, I don't know what, like $1 trillion or something. They haven't put $1 trillion in fusion. So I don't think we're trying so hard because there's no military application. It's the military, it's annoying, but when they put the resources, they make things happen. And we don't have that for fusion, so that's been a bit slower. Now we have global warming. We've got to do something about this. So that's a good incentive to do fusion.
Thank you, Toronto. I'm going to take a couple more questions here in Vancouver, and then we'll jump back to the Facebook Live feed. So I believe you have.
Thank you so much for the talk so far. So my question is regarding the public perception of nuclear fusion, because right now nuclear fission, from after Fukushima especially, countries are kind of going away from that. Do you anticipate any challenges convincing the public that nuclear fusion, which kind of sounds pretty similar, is a safe alternative and won't have the side effects that fission has?
This is a good point. Fission and fusion is so similar that even me, I say the wrong word all the time. We try to avoid the nuclear fusion. We call it fusion energy, although it is indeed nuclear. But the first reporter that comes will say nuclear fusion. So there's always a nuclear word. And yeah, people panic on nuclear, even if they don't fully understand the difference between fusion and fission. Physically, the difference is enormous. There is a bit of radioactivity in fusion, but it's millions of times less. It's actually very safe. But people don't know that. And this is a nuclear technology and it sounds the same. And we're going to get some problem with that. Yes, our PI guy has his job cut off. Yeah.
Awesome. We have one question over here.
Hi, thank you for your presentation and the lively discussion so far. My question is in regards to how you make sure that general fusion stays the best, and especially in the wake of so many competitors locally as well as internationally, and whether you think at any point that there's any room for collaboration between general fusion and some other of your peers or, in different parts of the world.
Well, collaboration-wise, we do collaborate with academia. Like fusion still, a large bulk of fusion is done by academia, like national lab and stuff like that. This company stuff, the private fusion is growing quite quickly, but still academic fusion is still a big chunk. And those guys, they're public, they got the money from the government, so they write paper, they go to conference. So we collaborate with those guys quite a lot. We would pay a researcher somewhere to do some research for us on something. So we collaborate with academic fusion a lot. Between companies, it's a little bit more tricky. There's investor, they want their return. They keep that a little bit more quiet. So that's a bit harder. There's 20 odd company of fusion, which they will not all succeed. So there will probably be some rearrangement over time. Like some will go bust, some will buy each other. It will, like when there's a shakedown in an industry. So I think there will be some of that in fusion. Yeah, we have collaboration with industry, and most companies collaborate with the academia. Between companies, it's a little harder. The competition, some will die, some will merge. How it's going to go.
And we have just a few more questions from the live feed. Nathan from SLX New Brunswick asks, how can students get involved with fusion development?
That's a good question. We do hire the odd people, and if we get money to build a big machine, we'll hire more. How can students get involved? They can get hired at different fusion company. They can go and work for the academia fusion. And I don't know, maybe they can try to spread the word, because fusion is not well known. And if they come in a position of some power in the government or something, make fusion known that it's a possible solution.
And Danny from SLX Ontario asked, can you speak a bit about the dynamic between companies in collaboration for fission or fusion projects?
Well, I answered that a little bit, just the previous question. But basically, the company collaborate with the academia, but company to company, it's a little harder. It's more like competition here. But academia, it's all public money and public result. Their result, they publish it. So we collaborate with academia.
Great, thank you so much. I'm going to pass the mic back to Lasia.
Oh, I get a goodie bag.
Yes. Unfortunately, that's all the time we have for questions. Sorry to everybody all across the country who didn't get their questions asked, but thank you to everyone who did ask. And thank you so much for coming here today and for being our keynote speaker. We have a little thank you gift.
Thank you
from the
very
network,
much.
And thank you very much.
All right, thank you.
Okay, Schulich Leader Network, we're going to take about a 10-minute break, and we're going to start promptly at 2 p.m. Eastern Time with our SLX Spark team competition. So we will be back at the podium with Danny McInnes and Aaron Pearston, who are going to introduce the 2019 SLX Spark competition. Thank you to Dr. Laberge for a wonderful presentation. Let's put our hands together once again.